Welcome, everybody. I'm Jadu Sibaraja. I'm one of the Pawsey Visualisation staff here at Pawsey. First, I would like to acknowledge the Vujak people of the Noongar Nation, whose lands where we meet on today. And I pay my respect to the elders past, present, and emerging. I also pay my respect to the elders on whose lands you are on today in Australia. So we are a small team at Pawsey, three of us, myself, Jesse, and Ali, who would be presenting today. We have three main services. First one is Nebula-based remote visualization, which is a Windows-based cluster, where users can do remote visualization on the Windows Nebula cluster. It is available to all Australian researchers and all university and public researchers. And the second one is the Visualisation Lab, which would be covered by Jesse, where users can visualize large-scale data on large visualization system. And the third one is remote visualization on Topaz, which is a Linux cluster. This is an extension of your supercomputing workflow where you can extend and start visualizing your data remotely at Pawsey. So which is somewhat similar to Nebula, except the fact is it's a Linux cluster. So we won't be covering in detail about remote vis, but we are more than happy to share some documentation if you want to know more about remote visualization. So our first speaker is Ali Zamani. He is a visualization specialist with extensive with engineering background and specializing in visualizing scientific data. He has particular experience in fluid flow, in porous media, in geoscience. At Pawsey, he is responsible for the Nebula cluster, including system as well as services. So if you are using Nebula or if you were trying to inquire, you would be probably get in touch with Ali. So over to you, Ali.
Thank you so much, Yatu. I share a screen. Please let me know if everything's working as expected. All good?
All good. All good.
Thanks. Thank you everyone for joining us today. I start with one of the very new visualization services at Pawsey that started to be in production quite recently. It's a cluster, as my colleague Yatu mentioned, meaning that the access will be in Windows environment. And the access is remote, so you don't have to come to center. Just to make it clarified, the access is remotely through the web. I start with introduction to the system and then giving some example showcases just to give you a clear picture on possible workflows or how you can use best of the Nebula. So first is system introduction and basically the configuration. As you can see here, basically we have in general two configuration, standard versus high-mem configuration. High-mem comes in double in RAM and GPU compared to the standard config, and higher config is available in only 5 nodes. We have one dual GPU as well. So basically access is upon the request. All of the nodes are dual core. Each core has 24 physical core. Hyperthread comes with, works out with 96 cores per node. It's very sophisticated and powerful system considering the latest generation of the NVIDIA quadro GPUs, A6000 and RTX 6000, coming with 48 and 24 gig graphic memory accordingly. Service highlights. The point, just to bold some points about the Nebula and differences between the Nebula and other systems. The access is truly web-based. So basically, at user end, you don't have to install any application, any client. Having a simple browser is enough, and accessing through the browser. It could be Chrome, Safari, Firefox, or whatever. It is touch enabled as well. So as long as you have a tablet and feel comfortable with the size, so that's enough to get it to the windows and set up your workflow and work with the application. It is Windows based, as mentioned before. Now is Windows 10, could be upgraded soon to Windows 11. Basically, any application could be requested to be installed on the cluster, and application could be requested at any time of the year, meaning there's no waiting time for application. Like, for example, supercomputer application are open at certain time of the year, but Nebula is basically open during the year, and whenever that you need access, just simply request. Use cases, basically, who's Nebula for? We can categorize the Nebula users in generally in 3 groups. If they have an application that only is available in Windows and they cannot run it on supercomputer. An example would be Avizo. I know Avizo has, for example, the Linux distribution as well, but the Windows one comes with better feature that some researchers are after those features. So still Windows is the preferred environment, and to use that, they need a very powerful, sophisticated, graphic intensive environment that they need to access, and Nebula would be the case. The second group would be those that they have applications running on supercomputer, but to submit the job, they need the GUI. What does it mean? It doesn't mean that they cannot access to that GUI directly from supercomputer. It is possible with very traditional methods that comes with their own downsides that I will explain in details if someone was interested. But those features, those downsides and issues are addressed in Nebula and resolved. So there won't be any issue like disconnection and sort of this problem in Nebula. The third group are the group that they are working with some application which has hybrid setup, meaning, for example, they have pre or post processing and computation or simulation in the middle. What does it mean? They need to do some pre-processing, for example, do meshing or design the geometry, and then send the data into supercomputer, do simulation on that, and then get the result back into the graphic intensive setup in the GUI to do visualization, as well as the other post-processing. I will show you some example in the next section, so you will have better idea what does it mean. How to apply? Basically, the application is pretty straightforward. It's single page application. You go to Pawsey application portal, which is web-based, apply.pawsey.org.au. You will request, and you will follow the rest of the process to get allocation. The point here I want to make it bold is that only supervisor or PIs can apply. So they will get allocation for their project, and they will get access to the web-based portal for managing their project, for adding members, removing members, or editing the privilege, giving admin access to one of the members, for example. So basically, you apply, you get allocation, and the rest of that, it's pretty straightforward. Could be manage it yourself. It's easy as this. And as I mentioned, at any time of the year, you can apply. There's no open date, for example. Feel free to send application after this presentation, and we'll be in touch with you. Getting access is, again, pretty straightforward. The UI is designed very simple, very straightforward and smooth. All you need is the reserving the system. It is a reserving-based or booking-based system. You go to reservation.pawsey.org.au, you apply, you book the system, and then you go to Nebula portal, which is nebula.pawsey.org.au, and you log into the Windows. It's as simple as this, and all done. Again, the important thing is that, as you can see here, Nebula is completely client-less service. You don't need to install anything at your end on your laptop. So the only thing is needed is a browser. How Nebula is integrated with other Pawsey systems. Some of you, maybe you are former Pawsey user using the supercomputer or Nimbus Cloud. So maybe you are wondering how to transfer the data, or is that possible to integrate or set up a workflow in a way that Nebula talks to the other services? Fortunately, yes, it is possible. And if you have any data transfer kind of task to be done, it is possible through Acacia. Maybe you have heard about that. It's the new storage facilities, which is in production quite recently. So regardless of you are using Nimbus Cloud or Supercomputing or Nebula or other Topaz remote viz that Yato was pointing, there's no worries for data transfer. So you can transfer data from other systems to Nebula and vice versa. That's one thing. And the other thing is the hybrid workflows that I was talking about for pre-post processing in Nebula and running the simulation on other systems. Yes, it is possible too, because all of those systems are connected with very high-speed connections. So you can submit a job through Windows and get real-time results on the go. And I will talk more about that in the coming slides. Basically, you do simulation on Cetonix, for example, you can get the same simulation results in the visualization lab that my colleague Jesse will talk about that at the end of this session. Please stay with us. And you can visualize the data, your data. So basically, everything is integrated together. Also, you can transfer data from home as well. You can see that it is connected to web with Acacia. Also, Nebula is connected to Nimbus Cloud, as well as the Cetonix, as well as the Topaz remote viz. So it's as easy as this. Now, showcases. I will talk about some of the examples that we have done here at Pawsey that will give you more clear picture how to use Nebula or the features of the Nebula, how you can get help from Nebula to set up your workflow more efficiently. The very first example is client server. The application, the specific application here is ANSYS. ANSYS is a very huge package, consists of different modules, CFD modules, as well as electronic and other engineering modules. It has capability to run the GUI and control the job running on the server from the GUI. So as you can see here, I played a video that shows you how does it talk to supercomputer. This is Windows, which is Nebula, and you set up all of the parameters And as you can see, you have 4 processors selected here. And in this part, you will put all of the configuration. And then when you start the job by importing your data, that will submit the job automatically on the supercomputer. So basically everything's happening in the background without any human interference. So everything's automatically done in real time in the background by a script. As you can see here, if you bear with me, submitted job here, it's shown, and sorry, bear with me. Yeah, and you can see you can have the same job submission here in supercomputer. No need to do this, just this is for demonstration purposes. Is there any problem, or still you can see the? Okay, I'll continue. I assume that you can see. Yeah. So by running the simulation here, you can see that simulation is converging here and is doing the simulation. And here you have the status bar, 12%, 13%, 14%. And if you go to the compute node, you will see those 4 processors, meaning 4 servers, are running and doing simulation in real time for you. Basically, you are getting the results back. Yeah, you can see that Fluent is the name of the application. For Fluent is running with the CPU of 100%. This is all for demonstration purposes. You don't need to do all these. Everything's happening in the background by a script. Basically, GUI runs in Nebula and pre-post processing, setting the geometry, doing the mesh, everything happened before job submission. You do submit the job, it happens on supercomputer. Simulation is being done in real time. You have overview of the job, which is progressing. You can see the results back in real time to make sure everything's correct. And if, for example, your case is not converging, it's diverging, you will cancel the job and you will save the time and resources, for example, as well as getting the results back automatically saved in Windows when the job is done. Job is done, you close the application and everything's saved in your user profile in Windows. So basically it's as easy as this. The second one is something I did with COVID open source data from Protein Data Bank. In Houdini, all of these new modern animation softwares, such as Houdini, Maja, that Maja will talk about that later, they are very well designed and programmed in very sophisticated way, and do all of these client server setup, apply all of these hybrid workflows easily, and get very nice results in shortest possible time with passing the simulation, not simulation, basically the rendering to be done on supercomputer on very huge number of the resources. The other use case is one of the projects that we have done here at Pawsey with Dr. Maja. By the way, we have 2 great speakers, Dr. Maja and Alexandra, that Wisdom was proud to be part of their project to help them to set up and do the research in Nebula. I won't go through the third use case, and I leave it to Dr. Maja to continue. And after that, Dr. Alexandra. They are more sophisticated in this domain as they have done it, and they were responsible for this research. So by that, I will pass it to Maja or Yatu, maybe?
Yeah. Thanks, Ali.
No worries.
Yeah,
Please feel free to send your question, whatever inquiry that you have in the chat, or stay with us after the session, and or contact us and we will be in touch with you. Thank you.
Thanks, Ali. Our next speaker is Dr. Maja Divjak. She is the inaugural biomedical animator at the Peter MacCallum Cancer Institute, where she is creating animations about cellular and molecular mechanisms leading to cancer. So her workflow is more in like using commercial software. Again, a different type of setup, but it's another kind of workflow, and interested to hear from her. Thank you. Over to Maja.
Thank you for that lovely introduction, Yathu, and thank you so much for the opportunity to speak today. It's indeed an honour. I will be talking about using 3D animation to explain biology. So I'll just give you an overview of where I'm going to take you today. I'll start by explaining what biomedical animation is and what it does, why it's important. I'll then take you through the process of rendering, which is one of the components of creating a biomedical animation. And then we'll have a look at the problem that I discovered when rendering our animation and the solution that Pawsey had on offer to try and solve this problem. We'll have a look at how the problem was solved and what the outcome was. So what is biomedical animation? Biomedical animation uses 3D animation techniques from cinema, so as you would have seen throughout Hollywood movies, to explain biology. And in this process, it accelerates understanding because it unfolds before your very eyes. It engages people with science because they can understand it, because they can see it. And as you can see from these 4 images, it shows us just how beautiful biology is. And this is what gets me out of bed in the morning, the fact that I get to work with these beautiful molecules all day long and I get to bring them to the world. So what does biomedical animation actually do? First and foremost, it makes the unseen world of molecules and cells visible. The only way you can see cells is with a light microscope, and the only way that you can see molecules inside cells is with an electron microscope, as Alexandra has so beautifully shown. But most people don't have access to a light microscope, let alone an electron microscope, which is a very large and complex piece of machinery that takes incredible expertise to use. So biomedical animation actually brings the world of molecules and cells to people in the absence of being able to use this kind of equipment. So you may ask the question, where do I get the information from? So how do I know what all these molecules look like so that I can animate them? And I rely primarily on data from a very large repository known as the Protein Data Bank, which you will find at rcsb.org. And most of the data that I work with is produced by a technique known as X-ray crystallography. And you can see over in the top right there is an example of an entry from the Protein Data Bank. You can see that there are lots of helices, coiled helices, and kind of parallel sheets at the top there, giving you an indication of what the structure, the internal structure of this protein looks like. So yes, primarily biomedical animation makes the unseen world of molecules and cells visible. It's also great for enabling understanding of new discoveries that might otherwise be really difficult to explain, particularly with text or with 2D images even. And it offers insight to scientists. I work primarily with life scientists who tend to think about their hero molecules in quite abstract ways. They think about them in terms of what they do and how they work, not really in terms of what they look like, what their structure is, and how they might fill space and the volume that they occupy. So when I'm working with a scientist and I actually am building their structures that they work with, when I show them to them, they're often really quite surprised, and they'll say, oh, I had no idea it looked like that. And what is this bit over here doing? And why does that stick out there? And so it inspires a lot of ideas in the scientists themselves about their hero molecules and what they might be doing and how they might be working. Also, biomedical animation is a visual presentation of biology that's not only useful because it's educational and engaging, but as we've seen, it can also be a work of art. The images are incredibly beautiful. So why is biomedical animation important? As you probably know, 60% of our brain is devoted to processing visual information and/or performing vision-related tasks. So we're visual creatures, and we have been since the days that we scanned our environment in search of food. But these days, with the invention of the internet and the complete rise and domination of social media, we are becoming increasingly so. And therefore, visual strategies are therefore the best way to engage audiences with science. And visual strategies are often the only way you can engage younger audiences with science. Biomedical animation also removes fear of science because it makes science accessible through the visual rather than overwhelming with abstract concepts, difficult language, strange jargon, which makes people turn 180 degrees in the opposite direction and run away. So it removes fear of science. At the Peter MacCallum Cancer Centre, we use 3D animation to enable our patients and the general public to understand molecular processes in cancer. So we have a whole universe of cells inside our body, and then we have a whole universe of molecules inside those cells. And they're all jostling around and communicating, and they're interacting without us having to think about it. And without us mostly even knowing of this world, most people are completely unaware of it. And biomedical animation actually connects us with this complex drama that's unfolding in our cells on a daily basis. And that sometimes this drama can go completely off script, for example, in the situation of cancer. It's also a really useful tool for explaining novel cancer therapies. And so at Peter Mac, we have been able to, or we've been recently licensed to actually produce what's known as chimeric antigen receptor T-cell therapy on site in the last couple of years. We're the only ones in Australia that are currently doing it. So the animation that I've created most recently in collaboration with Pawsey is all about this CAR-T therapy. And so it's a very useful process for actually explaining how novel treatments work. And just quickly, I'll explain what CAR-T therapy is. It is actually a process whereby you can take a patient's immune cells or T cells, and then you can re-engineer them to express receptors on the cell surface that specifically bind to cancer cells. So they seek out and bind to the cancer cells and then kill them. So this is a pretty amazing new technology. It's also a great tool for training staff and students about cancer biology and can be very useful for presenting scientific research at meetings and conferences. And it connects the lab to the public. This one is also very interesting because a lot of members of the general public tend to think that scientists are kind of odd people who wear white lab coats and they do nefarious things behind closed doors with their tax dollar. And so we kind of need to open the lines of communication to better inform what it is that scientists are doing in the lab. And biomedical animation actually gives a window into the research being conducted in the lab and is therefore a process of inclusion. So let's get into a bit more of the nitty-gritty technical stuff. What is the process of rendering in computer graphics? So in my case, each second of my 3D animations consists of 25 frames. Other people work at 60 frames, other people work at 24. And each of these frames consists of 1920 pixels across by 1080 pixels high, and that's a format known as 1080p. Other people again work in 2K and 4K formats. I work in 1080p, which means that there are just over 2 million pixels total in each frame that need to be created. And rendering is the process of generating each frame pixel by your software in your computer. And The images are generated from 3D models in your scene file, and the scene file also contains a lot of information about colours and textures, about lights and lighting, about depth, which gives perspective in your scene, about the position of the camera, and so on. So just quickly to confirm what compositing is, this is the process of then actually putting together all those frames in sequence to make a movie. So rendering, as you can imagine, can be quite a time-consuming process depending on scene complexity. And if we look over here, on the right here, I've got an image of a chimeric antigen receptor, and that's the model that I've got there in my animation software. And then if you compare what looks to be relatively simple with this image below left, this is a final output. You can see here that there are lots of these models here. They've been coloured and textured. There's a cell membrane added. There's lighting in the scene. You can see that there's perspective because of the depth that's been added, and there's information about the position of the camera. So you can see that going from that image on the right to your final image below, your rendered image, can be quite a time-consuming process, and it's often a bottleneck in the animation pipeline. So let's take a look at the software that I use, and I can't actually see the top of my screen, and the rendering problem that I had. So Autodesk Maya is the software of choice for me. It's industry standard animation software used throughout Hollywood, and it's fully customizable with scripting from the command line, which makes it very flexible and powerful. The rendering engine is known as Arnold, and that's a plugin that comes standard with Maya. And interestingly enough, it's named after Arnold Schwarzenegger. I also use a really amazing plugin called Molecular Maya by a group of software engineers called Clarify, and you can find them at clarify.com. And this plugin is amazing. You can import files from the protein data bank into the Maya software in various formats, such as atomic, surface, or ribbon. And it also gives you options to actually build molecular assemblies, rig them so that you can animate them, and also for synthesizing and animating double-stranded DNA. So I use that plugin quite extensively. However, I tried to do something a little bit out of the box with that plugin, and I really pushed the system to its limits, using particles to actually replicate atomic motion. So I did a lot of testing initially with some small scene files that had small frame numbers, and the render times were fine. There was no kind of obvious problem at all with these kind of smaller test scene files. Everything seemed to be great, and I thought, well, this is a fantastic method. It's going to work really well. Let's run with it. However, when I started to create much more complex scenes that were a lot longer, I tried to get a bit fancy and tried to render all my shots in one go rather than cutting them into smaller chunks and then putting them together. So I tried to do it all in one go, particularly passing from the external part of the cell to the internal part of the cell. So I had a lot of frame numbers I needed to render. And I found that render times became completely untenable with frame numbers greater than 1,000. And the problem was with the Arnold renderer having issues reading the particle cache files. So particle cache files actually store the information about the position of every particle at any given point in time, so that the computer doesn't need to recalculate each position at render time, and it makes the rendering process a lot faster. However, the Arnold renderer was actually returning to the beginning of each cache, the beginning of cache, to render each frame. So by the time I was getting out to 4,000 frames, I was waiting for up to 30 minutes for each frame to begin rendering, which was completely ridiculous. And I was forced to completely reevaluate the process and whether to abort the whole thing and think of something else, which was a really heartbreaking idea to have to deal with. But this is where the Pawsey came along. So enter the Pawsey. So our head of Peter Mac Research Computing, Jason Ilal, suggested contacting the Pawsey. And as luck would have it, they were in the development phase at the time of a new visualization system called Nebula. And they asked if I would like to become an early adopter. And I said, yes, I would love that. So the Nebula system has a couple of CPUs, 24 cores, 48 logical processors, 384 gigs of RAM, and fantastic NVIDIA graphics cards, 24 gig. And so it was powerful enough and fast enough to overcome these crazy cache cycling times, compared with my system, which had less than half the compute power of the Nebula system. So the other great thing was that I was able to access Nebula on a flexible basis. I was the only one using it at the time, so I was able to use it on an as-needs basis, which I'm sure is not the situation anymore, but it was great, it was very accessible. And they also provided plenty of storage for the rendered files. I needed at least a terabyte to be able to render and store those and then transfer them back to me here at Peter Mac. I also received incredible technical support from Ali Zamani, which was great. So solving the problem. Nebula was able to render 2 to 4 times faster than my desktops, depending on the frame number. So at around 4,000 frames, the wait times were reduced from about 30 minutes per frame to around 6 or 7 minutes. So it made a significant difference in the render time. And this meant that I was able to output all of my animation scenes and composite them into a movie, whereas trying to do this with my desktops, I'd still be doing it. It would have failed. So the production is currently almost at completion stage. So look out for that. It's coming any moment. And so the outcome was that I was able to achieve a beautiful final result in a timely manner using this quite computationally intensive atomic render method. I forged this great new working relationship between Pawsey and Peter Mac. And we're going to actually try our hand at rendering with the supercomputer to see if we can get things even faster, which would be even more amazing. The other lovely thing is that we've made others at Peter Mac aware of the service offered at Pawsey and the possibility of collaboration. And indeed, there are other groups here at Peter Mac that have made contact with Pawsey about analysing massive data generated from genomics experiments. So I'll just show you a little teaser, like an excerpt from the animation that I've been working on. So these are chimeric antigen receptors, and I'll kind of talk you through this. It probably won't play all that well over Zoom. So yes, it should play smoothly in real life, but it probably won't play all that well now. And it isn't. So I apologize for that. So these are chimeric antigen receptors, which are engineered on the T cell surface. You can see they have very long snake-like structure with a kind of beak-like head at the top here. That's the binding domain that allows those receptors to specifically bind to receptors on cancer cells. And so that's that portion there, that glowing beak-like structure. And if we pop below the cell membrane, we'll see that there are long snake-like structures waving around below the cell membrane, that is the signaling domain. And so once the binding domain has made specific contact with the cancer cell, the signal is sent inside the cell to the signaling domain, which then interacts with further molecules that tell the cell to go ahead and kill the cancer cell. So we can see we've got the binding domain of the CARs on the outside of the cell, and then the signaling domain on the inside of the cell. And of course, this will have sound design added, so there will be a lot of noise that you'll be able to hear that will punctuate the movement, and of course, a voiceover. So to summarise, as we've seen, biomedical animation makes the unseen cellular and molecular world visible, and it allows viewers to understand scientific concepts that can be really difficult to explain with text or even 2D images. Visual technologies such as biomedical animation are the best way to engage people with biology because we are so visually focused now. And we've learned that rendering an animation can be quite time-consuming depending on the complexity of the scene. And as I found, the Arnold renderer within my software had a big problem reading our particle caches that contributed to impossibly long render times. But being able to access the Pawsey's powerful Nebula system enabled much faster render times. So we were able to actually finish rendering our animated sequences. And indeed, our collaboration has paved the way for others at Peter Mac to work and collaborate with Pawsey. So I thank you for your time, and these are my acknowledgements. And yeah, thank you for listening.
Thank you, Maja.
Yeah.
Thank you, Dr. Maja. It's an excellent talk and very nice visuals as well. I've shared the case study here in the chat. Feel free to have a look. And our next speaker is Jesse Helliwell. He's a visualization specialist at Pawsey, and he has his background in computer science and game technology. He specializes in virtual and mixed reality simulations and visualization of multidisciplinary research data on large-scale displays. So here at Pawsey, he is responsible for the newly built Visualisation Lab, and he will go through the introduction of the system and what it can do. Over to you, Jesse.
Thanks, Jesse. Everyone can hear me all right, hopefully. We'll share my screen. So I would have loved to have been giving you this presentation from the Viz Lab so you could get a sense of the space. Unfortunately, I am in isolation. I don't have COVID, but 2 people in my household do. So I'm not allowed to go anywhere at the moment. But to give you an overview of the Viz Lab, that I can do and point you at the various resources for applying and you know, what you can do there, that I can do from here. So that's what I'll do today. All right. So this is sort of the main feature of the Viz Lab. It's so a large-scale visualization display. It's a CLED display, or that's kind of Sony's marketing term for it. It's a micro LED display. So this is kind of like the precursor to what you might see in your TVs maybe 5 years from now at a somewhat affordable price. At the moment, they're only suited to these larger scale applications purely due to price constraints. It's too expensive to miniaturize at the moment. So ours is a 72 module unit. That gives us a total size of around 4.7 meters wide and 2 and some meters high. And that is 4K UHD, so 3840 by 2160 in a 16:9 aspect ratio. One of the excellent features of the display is that it is 120 Hertz refresh rate and capable of active stereoscopic 3D, and purely due to the technology involved, it's some of the best quality 3D that you can really get. It's far better than anything you would have ever seen in a cinema, and the main factor behind that is basically a complete lack of ghosting or bleed through effects. The display switches from pure black to the exact color you want, and there's a gap in between, so there is no blooming from backlights as you would see in sort of normal TVs, no issues with contrast that you would see on a cinema projector. It's pretty close to the perfect sort of technology as far as displays go, and we're one of the first in the country to actually have access to this sort of display. The only other one that we're aware of is owned by Telstra, and they mostly use it for marketing. So we are the only research facility where you can come and look at your data in its full glory, I would say. This one should normally come after the other, but so one of the things that we currently developing at Pawsey is this idea or this paradigm of in situ visualization. So this doesn't just apply to the Viz Lab, but it's a key use case for the Viz Lab. This idea that you could be running your simulation, your fluid dynamic simulation or your bioinformatics simulations on Photonics, Magnus, in the normal way that you do, but then you can also be looking at that data in real time as it's being processed. So the supercomputer is also doing the visual component and sending that data directly to your machine at home or the VizLab machine, and you can actually see what's happening in real time. There's a couple of ways to enable that. As I said, it's a general paradigm, so you can theoretically implement this sort of concept in any of your various simulation workflows, but a few packages have kind of taken that and built a framework around it so you can do it much more easily without being a software engineer yourself. One of those packages is ParaView. So we support an in-situ workflow where you can essentially invoke the ParaView rendering library on the CPU render on the supercomputer or the GPU render if your cluster has access to GPU, and render out images in sequence in situ with the simulation as it's running. So you simulate a time step, you render the image, you can then chuck away all that huge amount of data that maybe you don't actually need. You would normally save it out to disk and then copy it to your local machine and a huge amount of data, and then make your visualization, and then you don't really need the numbers anymore because you've got your picture. So it can theoretically save a huge amount of data transfer and memory operations that you would normally have to do. So you make your image, and then if you're running a 12-hour long simulation or a month-long simulation, and you connect into it and you see that you've messed up a parameter or you're not getting the results you want, you can just cut it off right there and save yourself a huge amount of CPU time on the supercomputers, which is hopefully not with Photonics anytime soon, but with Magnus for a long time we've been fully utilized, and so the CPU hours come at a premium. So this is one of those ways that we can try and make workflows more efficient. And the takeaway for the Viz Lab is that you can do this stuff in situ, literally coming into the center and seeing what's going on the supercomputer that's just across the hall right in front of you. Another key application of the Viz Lab, we are in the process of sort of implementing a sort of virtual reality interface as well. So this can be motion controls with the display in front of you, but also with a head tracking headset. So the idea is that we will be able to, it'll be a space where you can develop your look at your research data. So if it's compatible with something like ParaView that has a VR plugin, or there's several other applications. And if it's not, then we can also help you with developing a workflow so you can take your fluid dynamic simulation, or you can take your geoscience data, and you can really get in there with the VR headset and look at it in detail that you probably haven't seen before. So I guess you could say it's kind of like Alexandra's data, where the researchers used to looking at it a certain way, and they see it in a whole different light once it's had access to that extra layer of visualization that and that can allow for new insights. And I've seen it in my several years of working between Pawsey and Curtin at the Hive, where we did a lot of this similar work with different large-scale displays in VR. Researchers are often blown away by the results. So other use cases for the Viz Lab, collaborative space, if you happen to be based in WA and somewhat local to the Bentley Curtin campus area. It can be, especially if you're collaborating across institutions, it can be a nice central place for you to have your research meetings and show what you've each been doing and that sort of stuff. Just as a collaborative thing between researchers. The immersive factor, so like I said, having your data up in that such a large scale can help you look at, if you're on your own little computer monitor on your laptop, then you'll often have to choose between looking at all of your data or zooming in and looking at a small amount of your data, but a large scale display really lets you sort of see everything at once, so it can help you sort of actually understand the structures better, depending on what it is you're doing, of course, and discovery. So that's pretty much what I just said, was enabling novel approaches to visualizing your data so that you can hopefully potentially make new discovery, not just making a pretty picture, but actually seeing something that you couldn't see before. So that's the sorts of stuff you do in the Viz Lab. I would normally have sort of demos to show on the screen, but since I'm not there, there's not really a huge amount of point. But if anyone is based in WA and is interested in utilizing the space for pretty much any reason, if it's connected to research, we are more than happy to talk to you. I'll link links to our application portal documentation so you can get a better idea of what the space sort of looks like and how you use it. And yeah, last thing I'll mention is that under the hood, in terms of the processing power that goes into this, it's Nebula nodes. So we have a Windows-based machine that you can access with the same specs as Nebula and dual GPU. And then we have a Linux-based system that you can access as well that's currently running CentOS, which is the same system that you'll find on our Topaz remote visualization cluster. So if your application workflow is Windows-based, you've got access to that. If it's Linux-based and you already have, say, a remote viz workflow, then you can bring it straight into the Viz Lab and it will just work. That's pretty much it for me. Thanks for listening. And I think afterwards we have questions. So for everyone.
Thank you, Jesse, for the introduction of the Viz Lab. As Jesse mentioned, if you are here in WA and would like to have a look at and go through, we can organize tours and show you what it can do. Questions. So I have some questions in the chat. The display is located at Pawsey Supercomputing Centre in Kensington, WA.
I remember one of the questions asking about the segmentation technologies or segmentation softwares. If that's okay, I can talk a little bit about that. For segmentation, all of these 3D medias comes out of the electron microscope as well as the microcity scanners needs segmentation. Without segmentation, you will have a mixed kind of phases of different cells in terms of the biomedical or different, for example, rocks in terms of the rock, if that's material science or geoscience. There are different techniques and applications for doing segmentation. I have a couple of the softwares here listed. At uni time, I was using ImageJ, and it was very basic, and an application, a plugin could be implemented in ImageJ called Veka. That was one of the first AIs, or one of the very basic AIs. I'm not sure at which stage is at the moment, but that was quite sophisticated at that time. Elastic is another one. These are the open source kind of application. We have Aviso package, Aviso Amira package, if you are familiar with. that's kind of material science package that does segmentation based on the threshold, if you are familiar with, which is not as accurate as AI. But basically, you can have your own code developed running on supercomputer or Nimbus, and then import the data results back into the Nebula or Topaz remote vis to visualize. It's up to you. I think that's very general question and could have wide range of answers in terms of the applications as well as the pipelines or workflows that we can go through the specific needs on that research project to go and design the best kind of solution. In many cases these days, many applications, either open source or commercial ones, they support kind of client server setup, meaning in a sense of having the GUI doing some pre-post processing, in this case, just designing a geometry, as I mentioned, ANSYS was one of them. You could do basically the same thing in Maja platform. It's called network rendering. It different phrases, different expression, and then you can submit the job on supercomputer to do the compute part for you.
Yeah, the other one was from Maja. She has answered. I think she was talking about what software was used for compositing and producing the movie in the end, or the labeling.
Yeah, I use After Effects, but there are many editing programs out there. Premiere is probably one of the more popular ones. Final Cut Pro, anything like that will work just fine. I like using After Effects because you can actually add a lot of sort of fancy film effects and so on. You can make it, look like Hollywood romance, or you can add vignettes and all that kind of stuff. So I find it quite powerful. I know you can do a lot of that kind of thing in Premiere as well, but yeah, it's just, I was trained on After Effects, so that's what I'm used to using. After Effects doesn't tend to play back all that well, so you can only kind of work with small segments at a time, and I actually have to output my whole movie by making a link between After Effects and Premiere and outputting from Premiere. So yes, I work with both. But I do all my kind of editing and adding labels and animated pointers and captions and vignettes and film effects and all that kind of stuff in After Effects. And then I just do the output with Premiere.
A very brief touch on the commercial softwares. Basically, you are free to bring your own application and request to install, whereas it's open source or commercial one. In commercial one, in case of Maja, that was which was commercial, the users are responsible for bringing the license. So as long as license is provided, we won't have any problem. License could be hosted at Pawsey or somewhere at your center, and then opening the port for Pawsey for checking the license and running the application. Just a very brief touch that don't be scared if you have license-based kind of software, all fine.
Yeah, that's correct. So everything that I was working with, so Autodesk Maya and Adobe After Effects is all license-based. So I just worked with you, Ali, and we installed it and got the licensing working. So yeah, you can do that quite easily.
Yeah, another question regarding the ability to kill the cancer cells. So what kind of cancer cell? And I know there are many different kind of cancers. Yeah,
so the chimeric antigen receptors that I've created the animation about, the ones that I have specifically created specifically bind to B cells, so cells that have a CD19 receptor on them. So they work primarily on blood cancers such as acute myeloid leukemia and diffuse large B-cell lymphoma. So there is an incredible area of activity at the moment trying to get this technology to work in solid tumours. It's very difficult to get immune cells into solid tumours. It's a very hostile environment. The T cells tend not to survive very well inside solid tumours. So this is an area of very active research at Peter Mac, is trying to get the whole chimeric antigen receptor technology to work in breast, colon and lung cancers, for example. But yeah, at the moment it works extremely well on blood cancers such as leukemias. And it can be completely miraculous. So people can be given absolutely no option at all. They have no option left and they're told that they have days to live. And then they're given this treatment and they completely recover. So it can be absolutely miraculous. And so it is being used in the clinic at the moment and it works. So yes, the next big push is for solid tumours. At the moment, it's, as I said, specifically being used for blood cancers, but we have many clinical trials in place testing variations on this system for solid tumours. So yes, it absolutely works in clinic.
There was a question around 3D stereoscopic rendering, if you have answered that one. So good.
I answered in the chat.
Jesse.
Yeah, okay. Sure.
Andrew was asked if Maja had done any of her renders in stereoscopic 3D. So we had, I already know the answer is no. We had very little to do with her workflow early on as an early adopter. She had a task she really needed to get done, and we were very happy to provide the system for her to do that. If we are involved in future projects, then you can be sure that we'll work with Maja to improve the speed of her workflow for our specific system, and hopefully that means we can get much higher resolution, higher refresh rate, stereoscopic images, and then they'd be excellent to display in places like the Viz Lab, places like Curtin Hive, and I'm sure there are similar high-end display systems. We were at, I think, in Melbourne, is it Maja? Where if you want to collaborate with them, then you can start showing people really immersive views of your research data, which I'm sure you'll appreciate.
Yeah, great.
A very final point on the system. Configuration wise, these are very sophisticated systems. So with 96 cores and up to 768 gig RAM and 48 gig GPU, if you double it, would be 96 gig graphic memory. These are huge and very massive kind of resources that you can do your work on independent machine. However, that would be more smarter and more efficient if somehow you we will help you with that to set up the workflow to run the rendering part or the simulation part on the supercomputer. That would be number of factors, many times faster. So this is in plan with Maja and maybe Belender with Alexandra. Unfortunately, we don't have Alexandra still. Yeah.
There was another question to Maja. Is the data for animation originating from computer simulations or experimental measurements?
No, it's not based on simulation data. So these structures are absolutely scientifically accurate. However, the animation, the movement, is created by forces within the computer. So I don't actually take simulation and feed it into the computer. I approximate it myself. Yeah, that is something I would really love to do, but I'd have to learn how to use Houdini, and that's for another lifetime, I think.
It's already here.
I know you use it.
Yeah, you can start. Yeah. That's very quick rendering on the core data that I did, but that would be much more beautiful with your skills and expertise. Yeah, so
feel free to get in touch with us at help@Pawsey, and thank you all for your time.